Thank you. Yes. Hello, everyone. My name is Michael T. Frucht. I'm doing a double PhD in philosophy and theoretical physics at University of Münster, and I'm going to discuss with you my work on the mereological aspects of thermodynamics. So it kind of fits to the previous talk. So the broad topic of my talk is the special composition question, which was introduced by Peter van Inwagen. So suppose you're looking at the table and you find there a book and you ask, okay, how many objects are there on the table? And you can say, okay, there's one object, namely the book. You can also say, okay, there are hundreds of objects, namely all the single pages that compose a further object, namely the book. And you can also say, okay, there are millions of atoms and they don't compose anything. That would be, so to say, the nihilistic answer. And the more general question is then, what are the necessary and jointly sufficient conditions for any set of x's for it to be the case that they compose something? And there are a variety of possible answers to that. So first of all, the extreme ones, namely universalism, which says they always compose something. Then nihilism, which says they never compose something, so there are only the only things that exist are entities without proper parts. There is moderate compositionalism, which says that there is a certain condition for the x's to compose. So Peter van Inwagen, for example, says it's forming alive. And finally, there is a brutal composition, which says, okay, there is no general condition. It's just a brute fact that the x's compose something. Now, that so far doesn't really have to do that much with science. But of course, you can also approach that from a scientific position, as we wish to do at this conference. And there is a tradition known as inductive metaphysics, which tries to analyze metaphysical problems in a way that is empirically informed, in particular scientifically informed. That actually has a very long tradition. It started in the second half of the 19th century. That is outlined in next test here, but of course it has become more popular in recent years, and therefore it's very interesting to look at the special composition question from a scientific point of view. So see if there are scientific arguments for being certain x's as composing an entity y. So an example is to say, okay, the x's compose something if they are in a bound state. This is something that I think independently has been proposed by Mackenzie and Müller and by Hußmann and Näger. And another criterion would be to say, okay, so quantum objects compose something if they are in an entangled state. So first you can have objections again, those kind of proposals, but at least they are quite reasonable, so to say. Those would be in the tradition of inductive metaphysics. So I'm going to start from thermodynamics, in particular from the minus first law. The minus first law was introduced by Brown and Iffing in this article here, and it says that an isolated system in an arbitrary initial state within a finite fixed volume will spontaneously attain a unique state of equilibrium. So there is one predicate E1, which stands for being in equilibrium. E1x that means x is an equilibrium, and minus first law says after a certain time it will be true that E1x. And very importantly, this equilibrium state is a unique property of the system X. Now in thermodynamics, you can find sentences of the form the system X is an equilibrium, and you can find sentences of the form the system X is in equilibrium with a system Y. So purely from predicate logics, you can already infer, okay, actually there have to be two different notions of equilibrium. And there's a one-place predicate E1 and a two-place predicate E2 being in equilibrium with. And two systems are said to be in equilibrium with each other if they are in thermal contact, but they do not exchange heat. And it's very important, as discussed here, they have to be in actual thermal contact. It's not sufficient, despite what is sometimes claimed, if they would not exchange heat if they were in thermal contact. And this relation is transitive as stated by the Zeeloff law. Now, a further principle that is also very basic, although it's not typically granted the status of a law, is given in these two quotes from Wallace. I'll take one of them, namely, multiple systems in perhaps generalized thermal contact may be treated as a single system. In particular, any such combined system will have a unique equilibrium state, And this quote says something similar. So if you have two objects and you put them in thermal contact, then you can treat them as a single object, and this single object then will reach a unique equilibrium state. This is quite standard in thermodynamics. You can find it in all textbooks, so to say, but it's not a metaphysically innocent assumption in some sense, because if it is true, then it would provide an answer, or at least a partial answer, to a philosophical problem, namely the special composition question, namely giving the answer objects compose something if though perhaps not if only and only if they are in thermal contact. Of course, it's not that easy, because it was pointed out by Brenner. There are a lot of cases in science where people work with composite objects, and that doesn't necessarily mean that a metaphysician should believe in those objects, because scientists don't usually consider, so to say, nihilist-friendly alternatives that do not involve composition. And therefore, we should say, okay, is this really the best description of the thermodynamic system? And probably the best way to do so is to just systematically consider all possible mereological models and then see which is the most appropriate one. So a systematic classification of mereological models was developed by Näger and Strohbach in this recent article here for the case of quantum entanglement. This classification can be used in pretty much the same way here for the case where the property we're interested in is having a unique equilibrium state. So what I'm going to do next is just go through all these models and see which is the best one for our purposes. So as an illustration, I'm going to use here this figure, which is from another article by Näger. So the 6 options are, first of all, moderate monistic holism. So E1, the property being equilibrium, is a property of the combined system. Suppose we have 2 systems A and B here in thermal contact, and the subsystems also exist. Then there is a radical monistic holism. So E1 is a property of the combined system, and the subsystems do not exist, or there's only one object in some sense. There is a moderate relational holism. So it can actually be reduced to the relation between the subsystems, and the combined system also exists. There is a radical relational holism. So E1 can be reduced to a relation between the 2 subsystems, and the combined system does not exist. There is a moderate pluralistic holism. So it's a collective property of the 2 individual systems, and the combined system also exists. And finally, radical pluralistic holism. So E1 is carried collectively by the subsystems, and the combined system does not exist. Okay, first of all, we go to the relational ones, so RRH and MRH, which say that E1 can be reduced to relation. So in principle, of course, there can be infinitely many such relations. We're just considering here the most plausible candidate, which is E2. So a system is in equilibrium if all its parts are in equilibrium with each other, so do not exchange heat with each other. This is something you can find in a lot of textbooks, actually, so it's kind of plausible. The problem is, as was recently shown by Mandal et al., there are systems, so-called underdamped active matter systems, which can develop coexisting phases with different temperatures. So you take 2 such systems, underdamped active matter, you bring them in thermal contact, and what would usually happen is, okay, the temperatures equalize, but in those systems, they develop a self-sustained temperature gradient. It does not change over time. Now, if we would define E1 in terms of E2, then this would count as an equilibrium system. But of course, that's nonsense, because that system does things that thermodynamics wouldn't allow, equilibrium thermodynamics wouldn't allow it to do. To get around this problem, we have to define E2 in terms of E1. So E2 can only hold between equilibrium systems. But then, of course, we cannot define E1 in terms of E2, because that would be circular. Okay, then we come to radical pluralistic holism and monistic pluralistic holism. Naeger in this article argues that RPH is the most appropriate model for quantum entanglement, saying, first of all, okay, quantum entanglement is a connective property, and then we do not really require the existence of the combined system. And in principle, you could probably run a similar argument here, but I would say in the case of thermodynamics, you do really need the combined system. The reason is that it adds explanatory value. So if you take these two objects here, one is cold, one is hot, and you bring them in thermal contact, you would say, okay, it's certainly prediction of thermodynamics. They will have similar temperatures after a certain time. But if you do not have composition, then that would not strictly follow from the axioms of thermodynamics, because the normal argument would be, okay, those two things here are a single object now. That single object will go to equilibrium by the minus first law, and therefore they will have the same temperatures. But if there is no combined system, then the minus first law doesn't apply. And the other laws don't predict the system to go to equilibrium, and therefore thermodynamics would not predict the system to go to equilibrium. It obviously does, therefore we require the combined system. However, and this rules out RMH, we also need subsystems. Namely, if they would not exist, then thermodynamics for composite systems would just be identical to thermodynamics for single systems. However, this is not the case because there are formal differences. This is discussed in more detail in this article. Namely, in thermodynamics for composite systems, you have more restrictions on how to define the entropy. For thermodynamics for single systems, you have a lot of freedom for rescaling it. This very, very sharply reduces in the case of thermodynamics of combined systems. And moreover, if the total system satisfies E1, then it is certainly true that these systems will then stand in the relation E2. Otherwise, the zeroth law really doesn't make sense anymore. So it is quite essential for thermodynamics that you also have the subsystems. And therefore, the only remaining option I would argue is MMH, so moderate monistic holism. And so this systematic analysis has brought us to the thermodynamic composition principle, which is a central proposal. Namely, there exists an object to Y with the axis composers if they are in generalized thermal contact. It's not necessarily a necessary condition, because you can maybe find other cases of other necessary conditions for compositions, quantum entanglement, for example. But I would say this is a sufficient condition. Then there's already quite an interesting insight because it would at least rule out nihilism if there is a sufficient condition for thermal contact, and would rule out brutal composition at least to a certain extent. Now, an interesting line of thought is you can say, okay, maybe that TCP gives us an argument for universalism. TCP is my abbreviation for thermodynamic composition principle. Namely, at least for systems on Earth, for astrophysical systems, you can say, okay, they are perhaps really far apart, but in general, most systems will be able to exchange energy in some direct or indirect way. And because it is such a general condition, it might be the case that the TCP implies universalism, namely by providing a condition for composition that is always satisfied, or at least it would sort of leave it for observation whether or not universalism holds, because we'd have to look empirically, does the condition of thermal contact hold between arbitrary systems? I'll come back to that later. First of all, I'll discuss some physical systems which you might take as counterexamples. Now, first of all, there are non-equilibrium systems. So classical thermodynamics describes equilibrium systems. So can we say anything about composition in non-equilibrium systems? And I would say yes, because the argument is based on the minus first law. And the minus first law is a statement about non-equilibrium systems. So it says a system will approach equilibrium, namely, which means it is not yet in equilibrium. or not necessarily at least. And therefore, the TCP allows to make a statement about composition also between non-equilibrium systems, like these two, for example. So fortunately, this one is still hotter than this one at the present time. And you can also show that it's discussed in more detail here that there are very special cases of the minus first law and soft matter systems, for example, that do have a microscopic derivation. Those are typically referred to as the H theorems in statistical mechanics. Okay, then there are small quantum systems. So historically, you would say, okay, thermodynamics has been developed as a phenomenological theory of steam engines, or more generally, macroscopic systems. And when it comes to very small objects, can we really apply arguments based on this theory, which probably is not really fundamental, or which you could then argue, yeah, that's not really fundamental, it's a macroscopic theory only. However, it turns out that the concept of thermal contact or heat flow can also be defined for very, very small quantum systems. So this article from 2019 is a very interesting example here. They studied heat flow between two single atomic nuclei. And of course, the two single atomic nuclei are far smaller than steam engines of classical thermodynamics, but still you can reasonably apply heat flow between them, and you can apply in a generalized way thermodynamic concepts. So I would argue that thermodynamics is much more general actually than it is usually thought, and you can, with certain technical modifications, still even apply it down to this scale. So in fact, quantum thermodynamics is it's a field of very active research at the moment. So this is a review article if you're interested in details. So I think the composition principle also applies in this domain. Then we come to anti-thermodynamic behavior. Here I'm coming to the problem of explaining the thermodynamic error of time from the microscopic laws of physics. The basic problem is that this is described in more detail in this article here. The microscopic laws of physics are invariant under time reversal, so you need an explanation for why entropy always increases on the level of the macroscopic laws. And a typical, and I would say a very plausible explanation is that it is due to the initial conditions, that is typically referred to as the past hypothesis. And if the thermodynamic error of time is a consequence of the initial condition, then you should be able to get anti-thermodynamic behavior if you choose the right, or depending on what you want, the wrong initial conditions. And that can be actually shown to be the case. So in this article here, we've performed computer simulations in which we artificially brought many particle systems, or in this case, system with about 8.5 million particles, into a state which is somewhat close to equilibrium, and that then moves away from thermodynamic equilibrium under Hamiltonian mechanics. So it is possible that a system moves away from equilibrium, and for smaller systems, you can even see that experimentally. So in this article, which I've mentioned before, they found that heat can spontaneously flow from a cold to a hot system if you correlate the spins in the right way. And you might say, okay, that is probably a problem for me because I'm using the minus first law as a starting point, and the minus first law doesn't really apply here. But I would say even in this case, I can rescue myself because there is still a unique equilibrium state, which you would expect the molecular dynamics system or the spin system to approach. It's just that in this case, it happens to be for these systems, it happens to be the case because the initial conditions that the system moves away from this state rather than towards it. But the state still exists. Yeah, now we come to astrophysics, namely the problem of self-gravitating systems. So gravity makes things typically very complicated when it comes to thermodynamics, and because a system that is dominated by gravity has negative heat capacity. That means if you bring a system that is dominated by gravity into contact with a hotter heat reservoir, it will transfer heat to its environment, then therefore it will cool down, it will transfer even more heat to its environment, and so on. This is so-called gravothermal catastrophe, which is not notably the equilibration you would expect from standard thermodynamics. Nevertheless, if you consider an actual star that is collapsing due to gravity because it has run out of fuel for nuclear fusion, then will finally settle to a state that is in equilibrium, so a white dwarf or neutron star or a black hole, depending on how massive it is. That is discussed in this article here. So you get equilibration also in this context, although of course in a much more complicated way. And finally, and this brings me back to universalism, there is the universe as a whole. So you can develop an argument for universalism maybe in the following way. So I've based the TCP on the observation that there is a unique equilibrium state of the combined system that it spontaneously approaches. And so if it is the case that the universe as a whole, and I'm meaning the physical universe here, approaches thermodynamic equilibrium, then we would have a reason to assume that the universe as a whole is a composite system, which again would be universalism, or at least something in the direction of universalism. And actually, it is a very widely believed scenario that the universe as a whole approaches thermodynamic equilibrium. There's a cosmological scenario known as the heat death of the universe, and was introduced in this article by Lord Kelvin, or at least around that time. So nevertheless, again, if you look at modern cosmology, it's probable that things are more difficult because the universe is expanding. So if you look at, so in this article here, it was argued that if you have an expanding universe, then yes, the entropy of the universe will always increase, but the maximum entropy of an expanding universe will increase even more, meaning that the entropy, yes, it does increase, but it falls behind its maximum value, so it will not approach equilibrium. So in some sense, it's so you say an open cosmological problem whether universalism holds according to the TCP. Nevertheless, even if you take into account such arguments, you can still say, okay, there are scenarios in which the universe reaches a state of eternal adiabatic expansion, which is very plausible, which is very close to what we usually imagine heat death of the universe to be. So the universe just becomes a dull, lifeless, uniform place. So there is hope, or no hope. Okay, so that was the metaphysical part. Now I'm briefly turning to the logical part, because I've also promised in my abstract formal analysis based on mereotopology. Mereotopology is a logical formalism that combines mereology and topology. It's an extension of first-order predicate logics with identity. And it is based on two relations, namely this relation here being part of, so this means X is a part of Y, and C, which stands for is in contact with. So CXY means X is in contact with Y. And those satisfy certain axioms. I'm not going to list them here. They are given in this book. And also there are different axiomatic systems which you can use for these two relations. I'm explaining that in a little more detail now. So if you have a sufficiently strong axiomatic system, namely an axiomatic system that is known as a closed extensional mereology, then you can introduce the so-called mereological sum of two objects, x plus y, which is, so to say, the minimal object that has x and y as its parts. And this allows you to define a self-connected object z, which satisfies this condition, which basically means that any two objects x and y that together compose an object z, thank you, form a component or are in contact with each other. And what that is intended to do is allows you to distinguish between joint and scattered objects. So this object and this object, so I'm supposing there is one object, may exist as composite objects, but this object here is sort of a whole in the sense that all its parts are in contact with each other, and this object here is a scattered object because it has this part, and they are connected, not connected to each other if you are ignoring B. So you can then gone back. You can then, if you consider contact also includes things such as contact via heat radiation, you can define thermal contact in this way, namely there exists an object Z that is self-connected and that X and Y are both a part of. And what that is intended to capture is that, so let's say there is a continuous path along which the heat could move from one object to the other for it to be possible that they can exchange heat. And then you can introduce this axiom that is also discussed in the book I've mentioned before, which says that if two objects are in contact, they underlap. Underlap means there's something they are part of, so basically composition. And one can then prove very easily that thermal contact entailed in this way, defined in this way, entails composition. So this is a logical way of formalizing the basic idea behind the thermodynamic composition principle. Yeah, and you can also make here an interesting form observation. Namely, I've mentioned before, you require certain axioms for it to be definable that there is a mereological sum. And if you have a minimal axiomatic system which does not allow you to define a mereological sum, then you can still attempt to define self-connectedness in a different way. In the typical way, which is then more complicated, is done here. This is defined here in terms of the overlap relation, which basically mean they share, so to say, a part. Nevertheless, and this is proven in my paper, it turns out that this definition here can also be satisfied by certain objects whose parts are not all in contact. So it's an artificial counterexample, but you can give a counterexample. And therefore, I would argue this definition of self-connectedness, in contrast to this one, is not appropriate for distinguishing scattered objects from joined wholes. And this is a problem for mereotopology also, or for weak mereotopology, so to say, also behind applications of thermodynamics. Yeah, so I'm coming to the acknowledgements finally. So first of all, I'd like to thank my philosophy supervisor, Paul Näger, who's also here today, who's introduced me to mereologically and who's supervised this work. Also my other supervisors, Rafael Witkowski from physics and Ulrich Groß from philosophy, and all the other people from the philosophy department and the mathematics department of the University of Münster, who have proofread the paper and the metaphysical arguments as well as the logical proofs. And of course, I'd also like to acknowledge my funding, which comes from the Deutsche Forschungsgemeinschaft, German Research Foundation, and the Studienstiften des Deutschen Volkes, so German Academic Foundation. And yeah, with that, I come to my final slide, namely I've shown that thermodynamics provides an argument for viewing thermal contact as a condition for composition, and thereby provides a new approach to the special composition question, and have also supplemented that by a logical analysis that was based on mereotopology. And if you want to read more details, you can have a look at this article. It has the same title as this talk here, and it is published on arXiv. And with that, I thank you for your attention, and I'm looking forward to your questions.